back to where we were. Let's just recap where we were. And last class, we spent the whole lecture talking about transition states. Right. Of course, the idea was very simple. We can define if we have some reaction that takes some number of reactants, we'll just assume 2, to form some set of products. We'll just say it forms one product. It doesn't matter. And we're going to assume that these things have some stoichiometry, so they're each multiplied by some stoichiometric coefficient nu. And we can draw this, we're thinking about this as a reaction along a coordinate, where we're going to track the energy of the system as a function of the reaction. And we start, of course, with A plus B at some energy. Our products, which may be delta G positive or delta G negative, I don't know, but our products are at some energy relative to the starting materials. And we know that in a general reaction, the energy increases and then decreases to the final product. And this height barrier we call the activation energy, E sub A, or we sometimes call it delta G double dagger. It's what an organic chemist would call it. E sub A is kind of our general term that physical chemists use. It's an activation energy. Delta G double dagger means a specific situation. You're at constant pressure. Delta G is well defined. We have entropy, we have a temperature, and so on. And activation energy is an intrinsic property of the molecule, right? It's how the energy transfers and how the energy increases overall as you break and form bonds. So it doesn't have anything to do with heat necessarily. And we saw that the rate of this reaction, right? We could calculate the phenomenological rate, the formation rate of the products, right? We just take a stopwatch and measure how much P we make over a fraction of time. And we said that this is equal to some rate constant times the concentration of A raised to the stoichiometric power times concentration of B raised to its stoichiometric power. And we have this nice equation for Kr, the rate constant, that's some number A, the prefactor, times e to the minus EA over RT. Right? That's the Arrhenius equation. All right, the Arrhenius equation turns out to not always be true. Once again, everything is an approximation. And where the Arrhenius equation is true or where it's false is actually a very, very subtle problem. And people, chemists and physical chemists in particular, love situations where this doesn't work. Because this is what you learn. You're like, oh, this is the way the world works. When you find the reaction where this doesn't actually apply, these could be really, really interesting problems. I've worked on some where Arrhenius is not something that you can assume. And of course, one of the assumptions that we're making is that things are at thermal equilibrium. There are ways to create reactions that are not at thermal equilibrium where this doesn't apply. So we do make some assumptions here, but again, we're not doing like what I would call, real physical chemistry, but we're not removing all of our assumptions. We can just still exist in kind of the mainstream chemical world where these things apply. And the idea here is that these coefficients on the rate law, they demarcate not the stoichiometry of the reaction, but they're the stoichiometry of the transition state. So if you have a reaction that involves 1 mole of A and 1 mole of B in the transition state, where 1 mole of A and 1 mole of B come together to form some new molecule, then the rate law is first order in both of them. But if it's a reaction where 2 A's come in and 1 B comes in, you're going to have a factor 2 here. Or if B has no role whatsoever, this new B exponent is going to be 0, right? So these determine the stoichiometry of the transition state. They don't determine the stoichiometry. They aren't necessarily correlated with the stoichiometry of the reaction, but rather the stoichiometry of how the transition state is formed. Okay. Those are sometimes correlated. Right? Sometimes reactions are this simple. You take an A and a B and they come together so that an SN2, for instance, right? The transition state involves both species at first order, 1-to-1. And we see rate walls as appropriate for SN2, where you have first order in both the reactions. But there are reactions like SN1 where that base does not play a role at all. And I want to look, but here's another interesting idea, is imagine you have some reaction that is, say, first order at some conditions, and it's only dependent on the concentrations of one of the products, the first order. The question is that always true for all conditions? Is a reaction that's first order when you go do it in the lab upstairs, first order in any lab at any condition, any pressure, any temperature? How does the rate change? Is Kr the same at every temperature, or is Kr dependent? Well, obviously Kr is dependent on temperature, so that's fair. But is it for instance, dependent on pressure? And is there some dependence where the rate depends on how much stuff you have in a given volume? And that maybe should make sense a little bit. Maybe there should be some pressure dependence on the rate. Because if you have a reaction like this, where you have A and B coming together, you can think that the chances that the system get to react is proportional to the number of times A and B meet together and fly. And so obviously, if you have some volume with some A and B in it, if you have more A and more B, your density is higher, then there's probably more likely more collisions happening. And if there's more collisions happening, then Kr is going to increase. So there must be some pressure dependence in the system as well. Kr is not just a function of T, but perhaps also a function of pressure or volume or something like that. And then you go and look at the Arrhenius equation and you say, well, where the hell does the pressure depend? We only have functions of T. Well, the important thing is that EA, right, is a fixed number. Right? It's something intrinsic about the molecules, independent of the conditions, molecular stability. So it's not there. It's not in T, obviously. Temperature is independent from pressure by definition. So it has to be an A. Right? An A, that prefactor, controls all the temporal aspects, right? It's the only thing that has units of time in here. Right? This has units of time. Well, it has inverse time. Right? So you can imagine that, well, if this is the thing that gives us a time, some base rates, then that must be the thing that varies with pressure, right? Because if you have more collisions per second, A should be larger. And so A, typically, the prefactor, A is not, I'm going to say is rarely a function of no variables. Well, let's say it's a function of no variables means a constant. That's a really complicated way to say a constant. But rather, A is a function sometimes of T and P as well. Right? And that's because A kind of, in a collision sense, tells you how many collisions happen in a second. Right? And the exponential factor in Arrhenius equation tells you the probability that one collision leads to a reaction. So A tells you how many chances you get, and e to the minus A tells you the probability of one of those chances being successful. So A has to have some function of A, T, and P as well. Right, so that means that as we change T and P, we will see the rate change, but if we keep T constant, we change pressure, we should also see the rate change. Well, let's explore that today. We're going to learn something by coming up with a really simple idea. We're going back into the literature and the history of chemistry. Find a really, really simple model that will allow us to start thinking about the dependence of the rates on the conditions. It's not just an intrinsic thing. And we're going to learn something really, really important about reactions doing this. So we're going to start simple. We're not going to put a bunch of molecules together and just let them go. Let's start simple and work our way up to complicated systems. So the first system, the example I want to study today is what are called unimolecular reactions. Right? And a unimolecular reaction, una means one, It's just a one molecule reaction. These are processes that look like some reactant A undergoing some decomposition or rearrangement to form P. All right, just one molecule involved. And we're going to assume this is, well, it's not a dimerization. It's not A plus A. It's just A. Right? So you can think of this as like a decomposition reaction. Right? What would be a good example of a decomposition reaction? Well, we've looked at one in equilibrium before. Right? The decomposition of PCl5 into Cl2 and PCl3. Right? Or a rearrangement reaction, something where a molecule moves around. There's lots of examples of this in chemistry. One of my favorites is the rearrangement between acetonitrile and what we call methyl isocyanide, where the C and the N flip. This is a well-studied reaction, very interesting. Surprisingly, a lot more complicated than you would imagine. But these are some ideas. And of course, there's lots of other types of composition. Lots of other ways. Just an idea. So I want to think a little bit about the kinetics of this reaction. Right? And you would say, okay, well, there's only one molecule in the system. The rate law should be trivial. Right? I could write down the rate law instantly. Right? By looking at this, I could say, okay, the rate of formation of P dP dt is equal to some rate constant times the concentration of A, raised to the first power. Okay, if that's what you would write in Gen Chem, and it would probably be a reasonable assumption. I want to teach you today why that's not a reasonable assumption. And I want to motivate this discussion with history, just a little bit of history. It's just an experiment. Is what when we talk about this is not a political conversation, right? Philosophical conversation. This is an interpretation of an experiment that was done in the early 1900s. Right? And what we're going to learn what's called the Lindemann-Hinshelwood mechanism for unimolecular reactions. Right? And Lindemann and Hinshelwood were kineticists. They were physical chemists in the early 1800s. I think Hinshelwood died pretty early on. I think he was the one who started this, and then Lindemann is the person who kind of filled in the theory. I can't remember if Hinshelwood was an experimentalist or a theorist. I don't remember. But they had a really interesting conversation in the 1910s about an experiment that Hinshelwood did with some colleagues. And there's a really cool paper by Lindemann and Hinshelwood called I forget what they call it. The Dalton. Anyway, it's like an argument paper where one person makes a statement and the other scientist in that paper responds and critiques it, and then they talk back and forth. It's like a conversational paper. And they talk about this reaction, and they come up with a really interesting result that we're going to study today. The example is really, really simple. Right? So what Hinshelwood does is he wants to start thinking about thermal decomposition of materials. So he has this reactor. Right? It's just a long tube that's sealed. He's got this flow tube, and he's got it such that there's going to be an active exhaust on the end, right? And then an active inlet for molecules at the top, right? So you're going to flow in molecules and have an active pump on the outside. So our flow rate, our molecules, our gas molecules will flow in this direction. And we'll have an active pressure here, active vacuum, right? So it's constantly sucking material out. So there's a net momentum to the air in this system. And so there's some flow, right, in this direction. Right? So you've got some gas and it's continuously flowing in this direction. Here's our gas particles. And they're compressing down here and getting sucked out. Okay, and we set this up so that this is at a constant flow. So we could say that on average that there's a steady state pressure inside of here, constant pressure. Even though molecules are leaving and coming in, the rate of leaving is the same as the rate of arriving, so the pressure equilibrates. So we'll say that there's some pressure here, steady state pressure, that is far, far less than an atmosphere. All right, a very dilute gas. Okay, so a low density gas. All right, and what Hinshelwood and Lindemann were thinking about is blowing these molecules apart with heat. So Hinshelwood's like, okay, well, how do we heat this up? Well, the logical thing, right, this is a stainless steel tube. Back then it was probably cast iron. Maybe it's aluminum. Just a normal old metal tube that's sealed. And he's just going to wrap a heating element around, like some heating coil. You can buy heat tape, for instance. It's just this fabric-like material that you can plug into the wall and it heats, control the temperature. So he says, okay, I'm going to take this system and I'm going to wrap it in a warming material that's temperature controlled. Right, so this is my heat tape. I'm going to draw it out. So I've got some heat tape here. I'll wrap it another time. And I've actually done an experiment like this before. Very, very similar idea. Very simple idea, right? So these are heating elements. All right. And what Hinshelwood wants to do is to look at these are A molecules. And I know, and Hinshelwood says, if I take like a sample of A, right, and I make it super condensed, and I put it in an oven at some temperature, right, he heats it up in like as a liquid or something like that, really, really high density material. Okay. You can think of a liquid sample or something like that in a small vial. Puts it inside the furnace and cranks the temperature up to 1,000 Kelvin, and he notices that the stuff decomposes. Right? He can't measure the kinetics of that because it's like a microwave, right? He puts it in, he knows he's heating it to some temperature. When it comes out, it's black and tar. So he knows it's reacted and decomposed. So he wants to do kinetics on it. So the way he wants to do kinetics on it is to take that material and vaporize it and flow it at some low pressure through a gas chamber that he can do kinetics on. Because the pressures are low enough that he would expect that the kinetics are slow enough that he can measure. Right? And he might have like a gas chromatograph or some detector over here that can detect the products. I'll make sure to add that, right? So this goes to a detector. Right, a modern instrument would use a mass spec for here, right? He might have used a gas chromatograph or a spectrometer or something like that. Lots of things. And he says, okay, well, when he does the high density measurement, right, when he takes a liquid or a solid and heats it, and he sets the temperature to 1,000 Kelvin, right? And this is high density, right? So we're saying the density is a molar scale, right? High density. And pressure equals 1 atmosphere, right? He sees that it converts to P, right? So he says, okay, so the hypothesis is crank heating elements. Let's say that this is effectively complete, right? He finds that it get 100% yield. Crank heating element to 1,000 Kelvin on flow. This is a flow reactor. And watch for P. All right. So we have some decisions to make. You've got to crank the temperature, but you also have to set the pressure. Right? We're going to say it's far, far less than atmosphere. Okay. And we're going to assume about this pressure that it's sufficiently low, right, such that the time of collision between particles and the time it takes for the particle to react, right? The two time scales is about even. Right, so we're going to turn collisions down, right? So we're going to have slow collisions. Right? He basically wants to turn the reaction off so he can see it come on as he changes the parameters. Okay, so he's going to drop the number of collisions, and so that the trickle of P is very slow, just enough that he can detect it over time. Okay, he doesn't want everything to crash out immediately. You can't measure kinetics with that if it's just an on-off switch. So he sets slow collisions. Right, he sets the heating element to a hot temperature. Maybe just to be safe, he raises it to 1500 Kelvin. Right, he knows that there's stuff's going to fall apart at 1500, it's falls apart at 1000. And so he goes to do that. He tries it at a high temperature. Right, no result. No P. That's strange. Right? He just explained that in his little vial reactor, a solid falls apart instantly. But then he does it in the gas phase, low density, to do a measurement, and it doesn't, no P forms, even though the pressure is right. Or sorry, the temperature is right. He in fact has more heat than he needs. In fact, he keeps cranking it up, the temperature up and up and up. And P maybe starts to form, but it forms in far less quantities than he would expect. Right? He says, oh, my activation energy is probably S. I have enough temperature to get over that barrier. Should be good. But yet it doesn't seem to happen. That Arrhenius doesn't seem to correlate with the results. Sorry, the gas phase data doesn't correlate with the condensed phase data. So Hinshelwood published these results, or whoever it was, and Lindemann and Hinshelwood had this nice conversation or paper about this. And they came up with an interesting realization. And I'm gonna prove that realization today. So how does the heat from these heating elements transfer into the gas? The first thing to think about is how does that heat the molecules? So what is the mechanism of heating? Right, well, the first thing is that the heating coils go to 1000 Kelvin. Okay, and then they transfer that heat to the surface of the reactor. Okay, that's efficient. That heating is efficient because it's an atmosphere. The air can contribute, and there's a good heating coefficient, thermal transfer coefficient between the heating coil and the metal. And of course, metals are good thermal conductors as well. Right, so this is an air, and metal is a good conductor, good heat conductor, and absorber. Right. So this is efficient, right? Right. So the surface of the material, the chamber, the tube is also at 1000 Kelvin. Right. Now we have an air gap. We travel, right? We have this tube now. So I'm just going to kind of do a cross section of the tube. And this tube, right? The surface of the tube is 1000 Kelvin. Right? But inside the tube is a low density gas. Right? The pressure is very small. Right? Pressure is much less than 1 atmosphere. Right? And then what did I say about the collision time? The collision time is extremely long. Right? And so at this limit, the rate of collisions, so collisions per second, is much less, that rate in some sense is much less than the rate of the molecules moving left to right, the flow rate. So what we have is a material where everything is just moving effectively in one direction and they're not colliding. They're moving like a traffic flow, a smooth traffic flow, and there's no collisions. So all of the gas is kind of flowing in that direction of the flow, right? And there's just not enough collisions. So there's no collisions with the gas. And because the gas is all moving in that kind of parallel direction on average, there's no collisions with the wall. Right? So how does that heat radiate? How can the heat ever equilibrate to the gas if the gas never touches the walls? Right? Remember, heat is being transferred in a system through collision. Right? That's how ideal gases change heat. That's how every material will change heat. But we're in a vacuum. Vacuum is extremely, extremely poor at conducting heat. Extremely poor conducting. The only way to conduct heat is through collisions of the wall with the gas. So the gas never equilibrates through collisions. So the gas doesn't warm up. Right? So that means, but is there any other, but the question now is there another way that the system can heat gas? Right? So it can't heat through collisions, but there's another way it can heat. So heat transfer through collisions is very poor, right? But the material, the metal surface itself is metal, or any material really that's at a temperature is emissive. It emits radiation at a given temperature. So there's an emissivity. The system is releasing radiation. It's releasing light, right? Because it's at a temperature, right? You know that, you might not realize this, but you see this every day. The sun, in fact, if you had a way to separate the light and measure the brightness of each color of light, the sun's most intense light is green. And the reason why its most intense is green is because that's correlated directly with the heat of the sun. The temperature of the sun determines the color. Just like you guys, if I were to have the right camera for you, you'd all glow in infrared, because things that are at 98.6 Fahrenheit emit in the infrared. When the trees emit in the infrared, you go look for an infrared picture of trees, they glow. They're bright because they emit so much infrared radiation because of the temperature. So what happens is that even though there's no heat transfer through collisions through mechanical action, there is some heat transfer through radiation. Right? So this system, these walls are radiating heat. They're radiating heat in waves, right, from the heat. But the walls radiate heat, right, as what we call black bodies. Black body emission. All right, we'll talk about black bodies next semester. That's a quantum mechanical idea, as it turns out. But this was known before quantum mechanics. How when people, the first way the sun's temperature was determined is through the spectrum of light. How we determine the temperature of any star, in fact, or the type of star it is by its temperature and its size. And therefore, we treat them with black bodies, and that teaches us a lot about the size and the heats that the star generates. But this is true for anything. Anything emits. But it turns out that as we'll learn next semester, that at 1000 Kelvin, the wavelength of the light, the radiation, the maximum wavelength of the radiation that gets emitted right? It gets emitted as light, is around 10 microns. Right, so the wavelength's about 10 microns. That's 2,000 inverse centimeters of energy, which is infrared, the far infrared. Okay, so when these walls are 1,000 Kelvin, they're hot to the touch. But when you get heated from them just from the thermal radiation, the only thing that you largely experience is infrared radiation. And you guys probably remember from organic chemistry, again, we haven't done infrared spectroscopy yet, that's next semester, but you maybe remember taking an infrared spectrum in orgo, that excites vibrations in the molecules. CH stretches and CC bends and things like that. It doesn't blow molecules apart, it just makes the bonds wiggle. So what that means is that this is the same type of energy. What this leads to is molecular vibration. Which is not enough energy to react. Not hot enough. Just say that, it's not hot enough. All right, so what Lindemann and Hinshelwood conclude is that if you wanted to do this experiment where you used an external heat source to heat up a gas to the point of decomposition, you have to go to thousands and thousands and thousands of Kelvin because the radiative mechanism for heat transfer is just not that efficient. You just lose a lot of energy to it because that heat that's organized that's consolidated in the metal has to get radiated out in all directions equally, and so it just gets filtered out, right? It's kind of diluted. The heat gets transmitted as waves over all frequencies and all directions. So that concentrated heat that you have in the material that a collision would suck up doesn't get nearly, it's not as nearly as concentrated per unit surface area as the emission of the light. So infrared radiation just isn't effective here. And so that the actual temperature inside the chamber is much colder than it is in the surface. Right? So if this is at 1,000 Kelvin, if this surface is at 1,000 Kelvin, then the temperature of the gas is only 600 Kelvin on the interior. There's a temperature gradient. So Lindemann and Hinshelwood realized this, appreciate this, and now they want to verify it experimentally. How do you verify that this is? Well, the claim is that the most effective way to get this stuff to react is for collisions. Collisions are a much more effective way to transfer energy between a surface and a material or between individual molecules. We want to do collisions. All right, and so what Lindemann and Hinshelwood has come up with a mechanism for how this reaction occurs that explains the results. That at low pressure, the reactions are extremely inefficient. And at high pressure, the reactions are much more efficient and go much more quickly and are much less sensitive to temperature than these ones at low pressure. So there's some pressure dependence to the kinetics. Because what happens is if you take this pressure to 1 atmosphere and you do this experiment, it works fine. Because the gas is colliding with the walls. It can transfer that air, right? Things with air pressure can transfer that heat effectively. So 1 atmosphere flow has no problem reacting, but a flow at say a microatmosphere or a milliatmosphere has much harder time reacting. So let's see if we can understand the kinetics of that. And Lindemann and Hinshelwood's mechanism for this is beautiful and simple. $2:30. Okay, that's right. This is Wednesday. We're out at 3:15. Okay. So the Lindemann-Hinshelwood mechanism. Right, and we're not going to keep it, we're just going to keep it simple. We're just going to think about A going to P, okay? It doesn't matter what A is, or it doesn't matter what P is, okay? We'll see that's completely general. And Lindemann and Hinshelwood write that the mechanism looks like this. The first step is collisional excitation, right? Increasing the energy of an atom of A or a molecule of A by itself or a non-reactive partner. All right, what do I mean by a non-reactive partner? Well, if this system has some helium in it, for instance, right? Maybe I have some helium in there, or some argon, right? Some gas, some air, or something like that. So like a noble gas. And what he says, what he claims is that so you take, let's just say 2 molecules of A, and they collide with each other and they exchange energy. And you create an excited A, which I'll call A star. This is our excited A. And the other A molecule loses some of that energy, right? This is what we call an inelastic collision, right? Some energy transfer from a collision, inelastic. And what is the kinetics of this? Well, we can write a rate law for this very easily. We could say that the rate of formation of A star with respect to time is equal to some rate, we'll call it K1, times the concentration of the reactants, which is A squared. Right? This requires 2 molecules of A to come together to form A star. We get second order kinetics here. Okay, so now what we have is this A that's now at some new state, new excited energy. Right? That has sucked that up from some collision. So what can A star do now? Right? A star is our intermediate. Right? So we're going to identify A star as a chemical intermediate. It is not a transition state. Right? For instance, imagine that A star is an ionization process. So you have A and A, and they come together to form A plus and A minus. Something, I don't know. Something else plus an electron off of A. Right? And this A star would be A plus, a cation. And there's nothing unstable about a cation. They're perfectly stable molecules, except for there are any situations where the cation is not stable. I don't know. I can't Google it. Right, so it doesn't have to be a transition state. It's just some intermediate state that may exist for a long time. It may not. Actually consider that. How long does A star last? So what can A star do? Right, we're now in a step into, we're now in an intermediate step. Right, we haven't gone just A to P. Well, we've taken A, we've converted it into some intermediate. What can A star do? Well, there's 2 options. One is we can just go backwards. Right? We should always have to consider, because of microscopic reversibility, the backwards process is just as likely as the forward process. Any action in physics can be undone with the same action done backwards in time. So A star can relax to A and return to step 1. So that would look something like A star plus, let me change my color. A goes to A plus A. Right? Just flip the reaction around, and we can write the same thing here. Right? Let's think about the rate of A star. Right? A stars are intermediate. Let's focus in on it. So we can write a rate for A star, but this is a loss. Right? Every time this reaction loses A star. So we get a negative sign here. And we'll say that it reacts at a rate K minus 1. We have K1 and K minus 1. They're inverses of each other. And it's proportional to the concentrations of A and A star. I minus sign. Sorry, there's a minus sign. I'll make sure to highlight that minus sign. That minus sign is important. Right? And again, I'm not doing anything fancy here. I'm just looking at this reaction. I'm saying this is some fundamental reaction, right? Some fundamental step. I'm saying the rate of whatever I'm interested in is equal to some rate constant. It's plus if it increases. If the reaction increases its concentration, it's negative if it depletes it. Times the concentrations of the reactant. I'm not doing anything special here. Right, and then there's one more step, right? A can go backwards, often, but A can also move forward, right? We can take A plus star and then react to form P. So there's one other way to remove A star, which is just to complete the reaction. And again, I'm going to write it in terms of A star. This is A star to P. And that's going to be equal to some new rate constant, K2, times the concentration of A star. Minus, because we're losing it. Okay. So what have we done? Well, instead of going from A to P, we've added an additional step. So we can draw a little coordinate diagram for this in energy. And we start with A, right? We can excite A to A star, right? There is a rate that goes up and down. Of course, this is K1 and this is K minus 1. And then we have P somewhere over here on the right. We'll say it's at lower energy. So it's exothermic. A star exists over the barrier. There is a barrier. So this is like A star over here. And there's some rate that converts this down, K2. So that's what our reaction looks like. Just 3 rates to do. Okay, well, now that's unfortunate in some way, right? Because now instead of having 1 rate law that I need to track, I have 3 of those. And the problem is that they all depend on a material, A star, that may be ephemeral. That may just be there for a very, very short amount of time, maybe a femtosecond, a picosecond. Might be there for a second, who knows? It really depends on the reaction. So we need to deal with that, right? We need to, right? We've made this reaction more interesting. We've also made it harder to analyze experimentally. So what we need to do is to think a little bit about how can we get this idea and morph it into something that we can measure in the lab. And how can we think about this whole reaction from the perspective of the 2 things we know, which is the concentration of P and concentration of A. And then can we get rid of this A star? Obviously, A star influences the reaction. But is there some approximation we can make where we don't have to think about it? Right? This is like the big take-home point today that I want to put. How do we analyze this problem? So we're going to apply an approximation to this process. Let's think a little bit about A star. Okay, A star has in some way 1 way to be created, right? So there's some rate of A star forming in this process. Imagine everything's just colliding randomly. So every once in a while, some A stars are made. And those A stars, well, once they're made, will quickly react to either form B or go back to A. Right? So you've got something that's increasing the concentration, right? You have some source of A star, but you also have a fast, efficient sink of A star. So you've got a rate that you have a rate for the concentration of A star that's increasing, but it's competing with one that is decreasing. Right? So if those rates are sufficiently fast, any molecule of A star you make immediately gets depleted to form P or A back. Right? So what that means is that any bump in A gets compensated with a decrease in A star. So what we can say about the concentration of A star is that it's constant. That there's always some constant amount of A star in the system because the related rates, the rate of formation and the rate of deletion, destruction, are equal to each other. So that means that the rate never changes. So we're going to apply an approximation. We're going to apply what's called the steady state approximation. To our intermediate. Right? And what is the steady state approximation? My claim is that A's rate of formation is fast, it's A's rate of destruction is fast, and so the total rate of formation of A, summing over all the creation routes and all the destruction routes, is equal to 0. Total rate is 0. Right? So what I can say is that I can say that the claim is, for this problem, is that the sum over all the steps of the rate of formation of A star dt, whatever that may be, that rate for each step is equal to 0. Okay. So the rate of formation, the total rate, what this means is the total rate of formation is fast, and it's equal to the total destruction rate. Okay. Well, all the rates. So all we have to do now is say, okay, the rates, if we sum the rate laws for the creation and the rate law for destruction, that whole thing should be equal to 0. Okay, so for our problem for A to P, so A to A star to P, we have to go back and look again. So our first reaction, right? Each of our reactions now are written in terms of A star, DA star, DA star, right? So the sum of all of these rates are 0. So we have K1A squared plus K minus 1 A star A. All right, that needs to be there. Plus K2 A star, right? That's our final step, is equal to 0. Oh, I have some negative signs, sorry. All right, we have some negative signs here. dAdt for the second step is minus, and it is for this third one too. Sorry, so these should be minus signs. Apologies. Right, and that should make sense, right? We have one step that creates A star and 2 steps that decrease it or destroy it. We have 1 positive term and 2 negative terms. And this whole thing should be equal to 0. Now look what I can do here. Right, I can now solve this equation for the concentration of A star, right? Because remember, we're at steady state. That means that the concentration of A star is fixed, constant. And we can see that I can now solve for A star here. Just pull up my notes. Oh, here it is. Yeah, this is it. And so we could say that the steady state concentration of our intermediate, right, is just solving this equation. We're left with K1 A squared over K2 plus K minus 1 A. What we get for solving this, and this makes good physical sense, right? We have a route for creating A star, and we have 2 routes for depleting A star. And A star's concentrations should increase if the formation route is more favorable or faster than the destruction routes. Right, so the numerator is K1A squared. That's the rate of formation of A stars from A. Right, so naturally the concentration goes up with K1. Likewise, if K2 the reaction rate is faster, the other collision rate, the reverse rate is fast, then the concentration of A star gets renormalized to a smaller number. Okay, so we have a competition here between destruction and destruction and creation, right? This kind of looks like creation rate over total destruction rate. But this is a really nice equation to have, because now I can write any of my rate laws that depend on this concentration. I can get rid of it and replace it with this number instead. Right, so now my A star, any A star dependence I have in my kinetics can be replaced with a combination of rate constants and some concentrations of A, things that I can measure. At least I hope so. Certainly I can measure the concentration of A. So let's put this together now. And we can write that again, the formation rate of the products, right? That's what we really care about, is equal to K2 A star, right? And I can bring in my steady state concentration of A star. This is equal to K1 K2 A squared over K2 plus K1 A. Right, so now I have a new equation. I have a new equation for my kinetics that isn't dependent naturally on just the first order in A, but it has second order dependence divided by the first order dependence. So depending on the values of the constants and the concentrations and the conditions, we may have something that looks second order, but we also might have something that looks like first order. If this is really big down here, then that A is going to cancel out with a factor of this A and you get A overall. Right? So we have some subtleties. There's some subtleties to the way that kinetics work now. Let's look at the two limits. We have kind of two terms down here that are competing with each other. K2, which is the reaction rate, and K1, this should be K minus 1, sorry, the reverse rate, are competing with each other. Right? This is the destruction of A prime back to A, the backwards rate, and this is the forwards rate. So let's think about the limiting cases. Let's think about this at two limits, the limit of low pressure and the limit of high pressure, right? That's what we really cared about in this reaction, because we noticed that the pressure considerably changed the kinetics of this reaction. Right, so let's assume, right, that collisional deactivation from A star to A dominates. Okay. Well, then that means that K minus 1 A, which is the thing that is much larger than K2. Okay. So this is a situation when there's lots of collisions. Right, that the A is constantly hitting itself, right? Just like your little brother hitting you, or your big brother hitting you. Stop hitting yourself. Lots of collisions between partners. But this is high P. All right, what happens? Well, if K1 is much larger than K2, so this product is much larger than K2. Well, if this number right here is 10 million and K2 is 1, then who cares if I write 1 million or 10 million or 10 million in one denominator? It makes no difference. So I can neglect K2 in that case. Right? And I get that dP dt. Right? What are we going to get? The K2 disappears. And now the K2 disappears, and now I have A over A squared over A, and I lose a factor of A. So this is going to end up being K1, K2 over K minus 1 times A. All right, so I get this product of rate constants, but that's just a rate, right? These are just rates. So this is some effective rate constant, Kf, K effective. It's something I can measure, right? It's a confluence of multiple effects or multiple events. But at high pressure, it's first order, right? It's A to the 1. It's first order. Exactly the way you would expect, right? Remember, the naive result we had for this was you have one molecule, the transition state can only involve one molecule, and therefore the kinetics have to be first order. So at high pressure, that's 100% true. But what about in the other situation? What if collisions are slow? So low pressure. Well, we have the opposite case. K2 is much greater than K1A. Right? And we lose the other term instead. And we get that the product formation rate is equal to, let's see, K1. Did I get this wrong? Hold on a second. So get rid of the K2. Oh, okay, K minus 1. So that goes away. So it's equal to K1 A squared. Right? Because the K minus 1 term disappears. This is small compared to this. K2 is to get destroyed. And now the rate is just dependent on K1. What is K1? That's the collision rate. So now the system is not dependent on some reaction rate, but it's now dependent only on the collision rate. And notice now it's second order. Right? The reaction requires two molecules to be there. That should make sense, right? In order to have a collision, you got to have two bodies. So the rate that's the slowest step of this process is the collision of two A's together. It's not a transition state, but it's the slowest step. And therefore, the rate depends on the rate of collisions, and it depends on having two bodies in the area. I agree. I'm surprised no one's told you yet to that. So let's put that together, right? So what's the qualitative conclusion about this? For a unimolecular reaction, success in reacting requires two bodies. It's not a unimolecular reaction. It's a reaction of one molecule that requires a friend. There's a buddy system involved here. So it's actually, so you could say that a unimolecular reaction is equal to a two-body reaction. Right? You need a reaction partner, you need a reactant plus a stabilizing body object that absorbs energy. Right? So unimolecular reactions, right? The reason why they're first order at high pressure isn't because they only need one body. It's because the collisions are so fast, you just neglect them. The slowest step is just forming the damn product. Right? But this still requires two bodies. We just assume that it's happening all the time, that it's no problem for one molecule to find a partner. But at low pressure, you don't have that luxury. In fact, at room temperature, and you're at, say, a microbar, a millionth of an atmosphere. The average time between collisions is 50 microseconds. 50 microseconds. Now, that doesn't seem like a lot of time, but compare that to a 1 atmosphere system. The collision rate is something like 3 orders of magnitude faster. There are thousands and thousands more collisions per second at 1 atmosphere. Actually, it's even more than that. I think it goes as, God, I can't even think about it now. It's a huge number. So what you're doing is you're really stripping things out. Molecules only collide with themselves as 50 microseconds. They only collide with themselves 20,000 times a second. It's not a lot of collisions. It's not a lot of chances. So naturally, they're just sitting there waiting for something to happen, something to come in and react. Now, in the last 5 minutes, I have just an addendum for this, something to think about. And we'll look at this next class, very brief. What if we go up a step? We go to A plus B. We have a bimolecular reaction. Well, now we've got 2 bodies, right? Great. Now maybe they don't need to worry about having an extra body because there's always a buddy there. So let's think a little bit about that. Right? What would that look like? What would Lindemann-Hinshelwood say? Right? What would Lindemann-Hinshelwood say about that? Well, they would say that what happens is A plus B maybe reacts. And maybe you form A star plus B, or B star plus A, or A star plus B star. You've got some options. And then they combine to form some AB intermediate, which then eventually falls apart to form P. Right? So we have excitation, addition, and relaxation to the final step. But again, these are equilibria. It's always possible for these things to go backwards. Once again, have we created a situation that's any appreciably different than we had before? No. Because ultimately, we now have a step where, well, in some things, 2 things have to happen, right? First, you have to get something excited. That's going to require a collision. Then you got to get them together, some high energy intermediate, and then you got to relax them, right? Where are collisions needed in this process? Well, you definitely need a collision here. I mean, you need them to collide here as well. And you need a collision there as well to relax. So nothing has changed, even at low pressure, even for a bimolecular reaction. At low P, the kinetics demand a steady collision partner. All right, so what's the conclusion then? Bimolecular reactions require a third body. For stability, for stabilizing intermediate. And also to generate it as well, but especially to stabilize the intermediate. All right, we'll look at an example next class of this. The fact of the matter is that this is one of those things that you don't learn. I didn't learn this until, I don't know, 2nd or 3rd year graduate school. But ever since I learned it, it's like one of those things, once you hear it, you always hear it. And it was my astrochemistry instructor And obviously in space, when you're forming molecules, you don't have a lot of collisions. For good reason. The average density of space is 1 hydrogen atom per cubic centimeter. There's not a lot of opportunities. Molecules can sit in space for thousands and thousands of years and never experience a photon or a molecule or a helium atom coming by. It's pretty rare. But how the hell do molecules form in space? Well, first of all, they don't really have, molecules don't typically form in space. They form on surfaces, grains, dust, ice, typically where they happen. But the reason why they're very rare is that you need 2 bodies, right? For a molecule to decompose in space, something has to come in to stabilize. A molecule absorbs a photon, the ultraviolet photon, and it gets excited and it wants to fall apart. But in order for it to fall apart, it needs some way to lose that energy. And the only efficient way of doing that is for collisions. Well, if there's no collisions, it never happens. So kinetics in space are very slow for that reason. There's just no collision partners. But we still think about unimolecular reactions because they occasionally happen over the course of millions of years, because there's, they do eventually happen, and there's light and there's eventually collisions, especially in high density areas. So they do happen. Now, bimolecular reactions, by and large, except for very specific situations, astrochemists, astronomers will say that we never consider bimolecular reactions. Imagine you have 2 molecules in space, methanol and acetonitrile. These are 2 molecules that are what my old boss would call promiscuous astrochemical molecules. They're everywhere. They show up everywhere. Carbon monoxide, for instance, molecule. Right? So you can imagine you have some place where there's carbon monoxide and methane or CH3. Maybe you can make formaldehyde or something like that. You have these bimolecular reactions of these 2 neutral molecules, CH4 or some ethylene, CO, like that. You can think of a reaction where they could react and form a new molecule. And you go in the lab and you do it. You show it to the astrochemist, and the astrochemist laughing. They said it'll never happen. Because even though methane and CO or whatever, they're in high concentrations in say dense regions of space, or say where stars are forming. But in order for them to react, there needs to be a 3rd body come in to stabilize them. Right? You have to stabilize that chemical intermediate. It's already hard enough to get 2 things together. Imagine getting a 3rd person to show up. And it's even worse than that. One of the things you maybe have learned in intro physics about orbits, you take 2 bodies, it's easy, you can find a stable orbit between 2 bodies. The 2-body problem is solvable in classical physics. So you can imagine you got 2 molecules floating around. Imagine they're like planets and they gravitationally attract each other. Imagine something classical like that. You have 2 bodies come around, they get close enough, they get locked into an orbit together. Right? So they can stay close to each other stably. Now with 3 bodies, you have to get 3 bodies to come together to form a stable orbit in the same argument. And what Newton shows is that there are no universally stable 3-body orbits. All 3-body orbits are metastable. Some of them last for a long time. For instance, the solar system's orbit of 9 bodies, 8 bodies for the Pluto deniers, and the Earth, that's a stable orbit. But technically it's not. There is a chance that the orbital structure of the solar system just falls apart instantly because it's not a stable orbit. And the reason why it exists in some sense, why we think we're in a stable orbit, is because we're in an environment where that's survived for a long time. So it's observer bias. But the fact of the matter is that it's exceedingly rare to take 3 bodies and to put them in some orientation, some trajectory where they all stably are around each other. One's just going to fly off, we're all going to fly off. And so if meeting together as a trio is hard enough already at low density, it's even harder to get them in an orientation where it's stable and they last a long time. So 3-body reactions, 3-body collisions just don't happen in low density environments. And so a lot of gas-phase chemists, we just don't think about bimolecular reactions because they just don't happen. They just don't happen. And if you want to study bimolecular reactions in the gas phase, you have to create environments that enforce collisions. And if I have some time, I'll show you guys this. But when we want to look at bimolecular reactions in the gas phase, what we do is we take a beam of A and a beam of B, and we move them perpendicular to each other so they collide. Right? We have a high density beam of A and a high density beam of B. We collide them together. And so instead of just flowing them together in a tube, we launch them at each other. And that experiment of that launching, what we call cross molecular beam reactions, where we cross things and react them, those are some of the hardest experiments in the world to do. There's a group in University of Hawaii that does it. Ralph Kaiser, he has a beautiful collision device where he studies these things in the gas phase. And his poor postdocs, oh my God, they have such turnover. He's always hiring like every 6 months. And I asked one of his people why that is. And he says, because the turnover rate's so high, because his lab works 24 hours a day. They have a day shift and a night shift. And the reason why is because the instrument's so finicky and so hard that you need 24-hour maintenance, 24-hour behavior in order to do these in a time efficient fashion. It's such a hard experiment to take two molecules and slide them together. Especially in chemical energy scales. Now, the physicists are really good at it, but they're exciting things to those people like exciting, so it's very different. So some important lessons about kinetics. Okay, so what we'll do on Monday. So with the steady state approximation in the Arrhenius equation, you can solve the entire problem set. What we're going to look at next class is to think a little bit about the transition state a bit more, and think about how can we lower or raise the transition state energy. How can we manipulate our reaction to lower the barrier or raise the barrier? That's what ultimately determines our kinetics. And the thing that lowers or raises an activation barrier is called a catalyst. It would be a really bad catalyst if it raised it. It's an inhibitor. So a catalyst is one that lowers the transition state. So we'll talk about catalysts next time. Talk about enzymes in medicine, maybe some solid state. Well, otherwise, you guys have a lovely weekend. Thanks, everybody. Hi, Angela. What's up? Yeah.
Because I was kind of doing it as you did. About as you're doing these things.
Yeah, sure.